All right, so in this video, we're going to learn a little bit about work and rotational kinetic energy. All right, all right. So we've already learned how to calculate rotational kinetic energy, right? Your rotational kinetic energy, that's a K, is always just 1/2 your rotational inertia times your angular velocity squared, right? And we know that torque on an object will produce angular acceleration, right? Because torque is I alpha, right? And so the idea here is that when you've got a torque on an object, that's going to cause acceleration, that's going to cause a change in angular velocity, right? Okay? So, in the same way that we learned that force causes a change in kinetic energy, torque causes a change in rotational kinetic energy. All right, so what's the connection? Well, one of the things we learned earlier this year was this. The work done by a force is equal to the magnitude of that force times the displacement. All right? Well, remember, displacement is just change in theta times the radius at which your displacement is occurring, right? Rearranging this, we can make this into force times radius times displacement, which is simply torque times change in theta. All right? So in English, suppose we've got a thing, right? And here's a pivot point, right? So the idea is if I apply a force here at some distance r away, then the displacement that that force undergoes is just going to be, delta x is what? Delta theta times r, right? Okay? And so that's sort of where this comes in. Okay? So this is exactly the equation that you would think it would be, right? Because to calculate work, you multiply force times the change in position, or angularly, the counterparts are, well, the angular counterpart for force is torque, angular counterpart for displacement is angular displacement, multiply them, you get work, okay? Now, just like with force, this only works if your torque is constant, okay? If your torque is not constant, then we go into this integration mode, right? And so work is the integral of torque with respect to theta, okay? And our work kinetic energy theorem still holds. The net work is still equal to our change in kinetic energy, okay? And we learned previously that you can calculate instantaneous power by doing force times velocity. That same equation now becomes torque times angular velocity, okay? So, probably the best way to do this is to do an example, all right? So you've got this example here in your notes. I'm actually going to skip this one for a minute because it honestly doesn't have a ton to do with what we just talked about there, so I'm going to jump ahead to this example, which may or may not be in your notes. All right, so take a second to write this down. All right, so what we've got here is a solid disk with a mass of 3 kilograms and a radius of 0.6 meters, all right? And what we're going to do is we're going to calculate the angular velocity that the disk will achieve, all right? So the idea is, because it's at rest, our rotational kinetic energy initially is 0, okay? So let's find our change in rotational kinetic energy. We're going to find the work done by non-conservative forces, okay? So the work done by non-conservative forces should be the magnitude of the non-conservative force times the displacement, right? Okay, so I just want to show you that you can do this either way and you get the same answer. All right, so it's through 8 full rotations, right? So 1, 2, etc., right? So our displacement there should be just 8 times the circumference, right? Because we're going to be pulling on this thing as this point goes through a circular displacement sort of 8 full rotations, okay? So we're going to have 8 newtons times our displacement would be what? 2 pi times the radius times 8, right? Right, so this is the circumference 8 times, right? So let's multiply that out, and we get, I need to grab my calculator here. What are we going to get? 64 times 2 pi times 0.6, and it gives us 241.3 joules, okay? Or we can do torque times change in theta. Okay, so what would our torque be? Well, the torque would be the force times the distance away from the pivot point, which is simply the radius, right? And then our theta is, so there's our torque, and then our change in theta is, well, it's going to go 2 pi radians 8 times, right? Okay, and you'll notice those are the exact same numbers that I had before in a different order, but it's clearly going to give us the same answer, right? Okay, all right, so what is this accomplishing? Well, let's see. Causing that wheel to rotate is not going to change the linear kinetic energy. Oops, it's not going to change the kinetic energy. It's not going to change the GPE, right? So that means that the work done by that non-conservative force must be a change in RKE, right? So 241.3 joules is our change in RKE. And since we began at 0, that means that our RKE final must be 241.3 joules, right? Okay, so now we just do, all right, well, let's see. RKE is 1/2 I omega squared. We got to take a second and find I, right? So I for a solid disk is 1/2 mr squared. So our mass was a number that I have forgotten, 3 kilograms. So 1/2 times 3 kilograms times 0.5 meters. Don't forget to square it. So you get 0.375. And so now we can solve for I, right? Let's see. Omega is going to be 2 times the RKE over I square rooty, just by doing some algebra. And so you get, let's see, times 241.3 times 2 square rootified, and you get 35.9 radians per second. All right? So there you go. That's pretty much it. If I give you a time, we could certainly find the average power, right? Average power would be work divided by time. Oh, let's do this. Let's find the instantaneous power. Didn't ask for it, but we can do it. Our instantaneous power is either force times velocity or torque times angular velocity. So our torque is, 8 newtons times 0.5 meters, right? No, 0.6 meters, sorry, is our radius. So there's our radius, and then times our angular velocity, 35.9 radians per second. So that's the instantaneous power achieved, at the end, right? So let's see, so times 4.8, and it gives you 172 watts. Okay, so not a whole lot there that's super enlightening, but you can certainly do work to change the rotational kinetic energy of a thing. All right, so let's go back and do another example. Okay, so this one is a system of objects. This solution is a little bit different from what I showed you guys in the last video. In the last video, we did this by looking at torque. This time, we're going to look at it as conservation of energy. Okay, so here we go. We've got these two masses. So here's what it tells us. It tells us that mass 1 is 0.8 kilograms, and it tells us that mass 2 is 1.2 kilograms. This disk up here has a mass of 0.6 kilograms and a radius of 0.05 meters. Okay? So the idea is mass 2 is heavier, so mass 2 is going to fall, mass 1 will go up, and the wheel will rotate, right? Okay? So let's do this in terms of conservation of energy, right? All of our forces are conservative forces. The only force here is gravity, and then tension, which is an internal force, and shouldn't affect the total energy of our system. Okay? So here's what I'm thinking. I'm feeling like, so as mass 2 falls, mass 2 is going to lose gravitational potential energy, and mass 1 will gain gravitational potential energy. But mass 2 is heavier, so our change in gravitational potential energy should be, well, let's see. Mass 2 is 1.2 kilograms times 9.8 times negative 0.75 meters, right? Because it's going down. And then object 1 is going to go up that that same distance, right? Okay, so if you multiply this all out, you get 3.92 joules, I think. I have it written down on a piece of paper here somewhere, which I have conveniently misplaced. It's 2.94 joules. I don't know what I did with my answer key. Okay. But it's negative, right? We're going to lose more than we gain. All right? Well, that means that that energy must be gained somewhere else, right? So that means that our change in KE and our change in RKE have to add up to positive 2.94 joules, right? Okay? So let's write an expression for that. So all I'm doing is I'm just saying that what was lost here must be gained here. Okay? So let's see. So our change in KE. Well, our initial kinetic energy was 0. So really all we care about is the final kinetic energy. So our final kinetic energy should be 1.2 kilograms times 1/2 times v squared. That's the kinetic energy of the 1.2 kilogram thing. Here's the other object. And then we've also got rotational kinetic energy. So let's take a quick second, and we're going to go up here and we're going to find I for this thing. So I is 1/2 mr squared, right? So we know our mass, we know our radius, so 0.3 times 0.05 squared, and it gives you 0.00075 kilogram meters squared. Okay? So plus, well, it's 1/2 times I, which is that number we just calculated, times omega squared. But I don't want omega, I want v. And remember, v is just omega r, which means that omega is v over r. So I'm going to put times v over r squared, right? Isn't that omega squared, this mess here? Okay. So if you simplify all of this, you end up getting 1.15 v squared equals 2.94 joules. Solve for v, and you get 1.6 meters a second. Okay? So that is that. Now, part B wants the angular acceleration of the pulley. Okay, well, we ought to be able to do that. Let's see. Let's find the linear acceleration of the masses. So here's what I know. I know that for the masses, I know that my VI is 0. I know my VF is 1.6 meters a second. I know my displacement is 0.75 meters. So we ought to be able to find the linear acceleration by using this guy. Right? So plug in your numbers. You'll find that the acceleration is 1.7 meters per second squared. And now we can simply use a jumper to find your alpha. Right? Alpha is a over r. So 1.7 meters per second squared over 0.05 meters. And it gives you 34 radians per second squared. Okay, so there's part B. All right, now part C. Part C wants us to find the tension in the rope on each end. All right, so much like that last example, the two tensions are no longer going to be equal. Sorry, when I say the last example, I mean the example from the last video. The tensions can't be equal, otherwise the net torque on the pulley would be 0 and it wouldn't move. Okay? So to find the two tensions, we're just going to do free body diagrams. Okay? So let me do this. All right, so for the 0.8 kilogram thing, here's what I know. I know that my force of gravity is 7.84 newtons, just 8.8 times 9.8. I know there's a tension force here. I know that that thing is going to accelerate up at 1.7 meters per second squared, which means that my net force is going to be that times 0.8. So it gives you 1.36 newtons, which you can then use to find your tension force, and it turns out to be 9.2 newtons. Okay? Now, doing the other mass gives us this. You got 1.2 kilograms. Your force of gravity is going to be negative 11.76 newtons. Now my acceleration is negative 1.7 meters a second squared, right? Because it's accelerating downward. Okay? And so the net force here turns out to be negative 2.04 newtons, which means that the tension on this end has got to be 9.72 newtons, okay, which is the two answers that were on the thing there. All right, now D wants us to use two different methods to find the net torque on the pulley. All right, so here's what we're going to do. Let me write down those two tensions. So the tension over here, let's call this force of tension 2, that was 9.72 newtons, and the force of tension 1 over here is 9.2 newtons. Okay, so that was dumb. All right, so let's find our net torque. All right, so option 1, part D, net torque is I alpha, right? So let's see, had we found I for this? Yeah, we had. I for this thing was 0.00075, right? So let's see, we know I is 0.00075 kilogram meters squared. We know alpha, because we already found it, is 34 radians per second squared. So multiply that out, 34 times 0.00075, and it gives you 0.0255 Newton meters, right? Or we could do this. The net torque is the torque from force 1 plus the torque from force 2, which is 9.2 newtons times 0.05. And then one of them needs to be negative. Let's call the direction of acceleration positive. So I'm going to make this guy negative plus 9.72 newtons from the other force times the same lever arm. And multiply that out, and you get the same answer. Oh, it doesn't turn out to be exact because we rounded some numbers off. But it's pretty close. All right, so there's our net torque. All right, find the average power delivered to the pulley. Well, we just want to find our change in rotational kinetic energy per unit time, right? Just to the pulley, okay? So, so to do this, what are we on, part E? Change in RKE over time. So our RKE is 1/2 I, which is 0.075 times omega. Let's see, we haven't found omega yet, but we did find the V. So omega is V over R. So the V we got was 1.6 meters a second divided by our radius gives you 32 radians per second. Don't forget to square it. And then divide it by, oh, we got to find the time. Who wrote this problem? All right, so, so let's see. I feel like we can do this. VF minus VI over A, right? Our VF is 1.6 meters a second squared. VI, oops, just meters a second. Minus 1.7 meters per second squared is our acceleration. So this gives you 0.94 seconds. So now we can just divide by 0.94 seconds. So divide it out and you get pretty close to 0.4 watts. Okay? And then the instantaneous power, well, that's just, well, I guess we just do force times velocity, right? So the instantaneous power being delivered to it for part F, power is force times velocity. Well, our net force is negative 9.2 plus 9.72, right? Times the velocity, which was 1.6 meters a second. So, let's see, 0.52 times 1.6 gives you 0.832 watts. If you wanted to, you could also do torque times the change in theta, and it amounts to the same thing, okay? Because we found the net torque in part D, right? And the change in theta would be, you know, whatever corresponds to 0.75 meters. Well, let's do it real quick. Why not? So let's see. Delta theta equals delta x over r. So 0.75 meters is how far it fell. The radius is 0.05. 0.75 divided by 0.05. So that gives you 15 radians times the torque, right? So our torque was 0.026 times 0.15. Why am I uneasy about this? Oh, that's not right at all. Try that again. Power is torque times velocity. So our torque was 0.026 Newton meters. Let's try this one last time. Power is torque times angular velocity. There we go. So 0.026 Newton meters was the torque that we found earlier. Our angular velocity was 32 radians per second. So multiply it, and that does in fact give you 0.832, or somewhere thereabouts. Let's see, 0.026 times 32. Well, gives you exact. Cool. There we go. All right.